A warm welcome to all. Myself Jijin KM, Assistant Professor, Department of EEE, Vedavyasa Institute of Technology. Today I am going to discuss about the topic Integrated Bidirectional AC to DC and DC to DC converter for plug-in hybrid electric vehicles, otherwise it is known as PHEV. So as we know that the electric vehicle is a relatively new concept in the world of automotive industry, and conventional gasoline vehicles produces a lot of carbon emissions that are injected into our natural atmosphere and leaving us vulnerable to things like pollution, greenhouse gases, etc. So in order to positively help the environment we live in, an electric vehicle is a great step forward. Vehicles can be classified into gasoline vehicles as well as electric vehicles. These electric vehicles is again classified into hybrid electric vehicles and non-hybrid electric vehicles, and this hybrid electric vehicles is again classified into conventional hybrid electric vehicles and plug-in hybrid electric vehicles. Actually, in hybrid electric vehicles means it uses both gasoline as well as battery for its operation. But in conventional hybrid electric vehicles, gasoline powered internal combustion engine is the main power source. In plug-in hybrid electric vehicles, the battery powered electric motor is the main power source. That's the difference between these conventional vehicles and plug-in hybrid electric vehicles. Actually, in general, in electric vehicle, the heart of the electric vehicle is its battery. So the battery should be charged from a charging station, but we can't give this direct power from this charging station to this battery. In between, the converter should be there. So we are giving the power from this charging station to a converter, and it will convert this power to a level which is suitable for this battery. Okay, that is the first stage of operation. Then coming to the second stage of operation, the energy in the battery has to be given to the motor of this vehicle. So we can't give direct power from battery to that motor. In between, there should be a converter. So that is the second stage of operation. Also, in regeneration mode of this motor, the power has to be fed back to this battery. So regenerative operation. In that case, also one converter should be needed. So this is the third stage of operation. So in a conventional hybrid electric vehicle, the three operations are done by a separate converter circuit. So it makes the system bulky, costly, etc. But in plug-in hybrid electric vehicles, here I am discussing a topology or a converter. It's an integrated bidirectional converter which deals with all these three operations in a single circuit. That's the advantage of this topic. Coming to the block diagram of the discussed converter, the upper portion shows the converter and battery, and lower portion shows the D space, which is a control of the circuit. And the circuit consists of full bridge rectifier, bidirectional integrated converter, battery, gating signal unit, signal isolation stage and current feedback unit, plug-in hybrid electric vehicle. If our charging station is AC type, then a full bridge rectifier is used to convert this AC into DC, and the DC power is given to bidirectional integrated converter. And this bidirectional integrated converter has three modes of operation, that is mode 1, mode 2 and mode 3. In mode 1, DC power is used to charge the battery, and in mode 2, battery power is used to drive the PHEV, and in mode 3, the power is fed back to the battery from the PHEV. All these three modes of operation works based on the switching of the switches used in the bidirectional converter. Actually, there are many topologies available for plug-in hybrid electric vehicles. Then why should we use this topology? What are the importance of this topology? Coming to this topic, it deals with three levels of voltage, that is the plug-in voltage, the battery voltage and the high voltage bus of HEV, and the three stages of power conversion can be done using a single converter. Actually, I already discussed about the three stages of power conversion. The first stage is the battery charging stage. In the second stage, the power is given to the HEV from the battery, and in the third stage, the power is fed back to the battery through regeneration. So all these three stages of power conversion can be done by using a single converter, that is our integrated converter. A single power inductor is used here. Number of current transformers used is 1, so cost effective and not bulky. Coming to the circuit diagram of the discussed converter, it consists of 6 switches from Q1 to Q6, 6 diodes from D1 to D6, 1 current transformer CT, 1 inductor L, 1 battery and 2 capacitors, and a rectifier unit and a D-space unit for controlling. The gating pulses for all the 6 switches are given by the D-space unit. The integrated converter consists of 3 modes of operation, that is mode 1 operation, which is also known as buck or boost mode of operation. Mode 2 is the boost mode of operation. Mode 3 is the buck operation. In mode 1 operation, The rectified power from the rectifier is used to charge the battery. So it acts as a buck or boost mode of operation. Mode 1 operation is only possible if the vehicle is standstill. Mode 2 and Mode 3 operation is possible when the vehicle is in running condition. In Mode 2, the battery power is given to the PHEV so that the converter acts as a boost converter. Mode 3 is for regenerative operation. That is, power is fed back to the battery from the HEV. So it acts as a buck converter. Coming to the Mode 1 operation, it consists of both buck and boost operation, and the buck or boost operation is determined by the battery voltage VVIT and the input voltage Vin. Here switches Q1, Q2, Q3, diodes D1, D3 and inductor L1 make up the non-inverting buck boost converter, and switches Q1 and Q2 are in PWM switching mode and Q3 remains in the on state during the operation. The input-output voltages and inductor are measured through RS1, RS2, RS3, RS4 and CT1 respectively. During the buck operation of Mode 1, switch Q2 is always off and Q1 is in PWM mode and Q3 is always on. So when the pulses for Q1 goes high, the inductor will store energy through the path Q1, CT1, L1, T3, Q3, battery, and again it will complete the path. You can see that in red rigid line. Whenever the pulses for the Q1 goes low, diode D1 is coming to the picture. The inductor will release the energy through the blue dotted line. That means output voltage is always less than that of the input voltage, so it will be in buck mode of operation. During the boost operation of the Mode 1, Q1 and Q3 is always on and Q2 is in PWM mode. Whenever the pulses for the Q2 goes high, inductor will store energy through Q1, CT1, L1, Q2 and again return back to the path. Whenever the pulses for the switch Q2 goes low, inductor will release the energy through Q1, CT1, L1, D3, Q3, VVIT and again return the path. So the output will get an input voltage plus the inductor voltage. So the output voltage is boosted. This I already explained. This is the Mode 2 operation. That is, battery is giving power to the high voltage bus of HEV. Here, battery voltage VBAT and high voltage bus of HEV, VHEV sequentially become input and output voltages. Switches Q2, Q4, Q5 and diode D4 and D5 from a boost converter. In that, VHEV is higher than VBAT is assumed. And Q2 is in PWM switching mode and Q4 and Q5 are in the on state. The other switches and diodes Q1, Q3, Q6, D1, D3 and D6 maintain the off state to supply the AC outlet. The input-output voltages and inductor current are measured through RS3, RS4, RS5, RS6 and CT1. Whenever the pulses for Q2 goes high, the inductor will store energy through L1, CT1, D4, Q4, VBAT and again Q2. And whenever the pulses for Q2 goes low, the battery voltage plus the inductor voltage will appear across C2. So you will get a high voltage across high voltage bus of HEV. So this is the boost mode of operation. Next is third mode of operation, that is buck operation for regenerative charging of the battery. Here power is fed back to the battery from the high voltage bus of HEV. Here switches Q3, Q6 and diode D1, D3 and D6 are used for the buck converter, and that of VHEV higher than VBAT is assumed. Q6 works for PWM switching, Q3 stays in the on state and D1 provides a freewheeling path. Other switches and diodes Q1, Q2, Q4, Q5, D4 and D5 are in the off state. To sense the input-output voltage and current, RS3, RS4, RS5, RS6 and CT1 are used. Whenever the pulses for Q6 goes high, inductor will store energy through the path VHEV, Q6, D6, CT1, L1, D3, Q3, VBAT. Whenever the pulses for Q6 goes low, inductor will release energy through L1, D3, Q3, VBAT, D1 and L1. That is, diode D1 is coming to the picture. So the output voltage is less than that of the input voltage and it acts as a buck mode of operation. Now I am concluding this topic by giving a short summary about this topic. Integrated bidirectional converter for plug-in hybrid electric vehicles (PHEVs) is a new method of charging of battery pack and energy conversion from battery to high voltage bus of PHEV. An integrated converter has less cost, volume, weight and less number of current transducers and high current inductors. The converter has three operating modes. They are plug-in AC to DC charging of the battery, boost operation from the low voltage add-on battery to the high voltage bus of PHEV, and buck operation from the high voltage bus to the add-on battery of regenerative charging. The converter discussed here can implement 3 tasks by sharing switches and inductor in all-in-one system.